We are down to our last two tests. I think if you count, this would make number 9 and 10. We're going to look at the ratio and root test. So we have a series that has non-zero terms. The series converges absolutely when you take the limit of the ratio of the next term divided by the previous term. And that limit has to be less than 1 in order for it to converge absolutely. Now, that word absolutely just means you've taken that absolute value, you've taken out any possibility of any negative terms. The series diverges when that same limit is greater than 1, and greater than 1 would include infinity. The sad thing is the ratio test is inconclusive when you get a limit equal to 1, which happens. A big help is you should always use the ratio test if you have factorials. It's also very helpful if you have powers of n. The root test looks almost the same. Okay, again, converges absolutely because we're going to take the absolute value of the series and we're going to take the nth root of it. And if the nth root, that limit, is less than 1, just like the ratio test, then it converges absolutely. The series diverges when that same limit is greater than 1, which includes infinity. So just like the ratio test. And so, in fact, I have a typo. I probably copied and pasted. The root test is inconclusive when that limit is equal to 1, which means you have to try something else. Now, when should you use the root test? The only time you should use a root test when everything is raised to the nth power. Because then when you take the nth root of that, you would just be left with that. That doesn't happen very often. So let's look at a few examples. Number 1. You see how you've got lots of jumbled stuff, you've got powers, all kinds of things. What should we do first? Well, I don't want to use the root test because I don't have everything to the nth power. I have powers of n, so I'm going to use the ratio test. So what does the ratio test say? It says take the limit as n approaches infinity of the absolute value of the ratio of the original, which goes in the denominator, and what goes in the numerator is everywhere there was an n, you're going to put an n plus 1. Everywhere there was an n, you're going to put an n plus 1. Now that looks kind of scary. So I'm going to suggest instead of writing the limit like that as a ratio, let's go ahead and rewrite it as the n plus 1 term. And if you're okay with this, that's just going to be n plus 2. And then dividing by the original one, which means I'm going to multiply by that reciprocal. And writing it like that, I think you're going to see how it's going to help us reduce. Okay, so first of all, here and here, we have the same base, so we can keep the base and subtract the exponents. So remember, this is 3n times 3 to the first power. Remember, keep the base, add the exponents. So I can divide that out, and I'm left with a 3. Same thing here. Okay, so this is the same as 2 to the n times 2 squared, and this is 2 to the n times 2. So those divide out, and that just leaves you a 2. So what have I got left? I have that. Do those divide out? No, they do not. So let's see. I have the limit as n approaches infinity. I have that 2 and that 3. Pull that out. And all I have left with is n plus 1 squared over n squared. Now can I take that limit? Yes, I can. So again, we have the same power, coefficient. So that is going to approach 1, and you're going, oh no, that's inconclusive. No, because I'm still multiplying by that 2/3. So that limit is 2/3, which is less than 1. So therefore, the series does what? It converges by the ratio test. In fact, because I took the absolute value, I can even say it converges absolutely by the ratio test. All right, let's look at number 2. Do I have everything raised to the nth power? Well, if I rewrote this, I could write this as from 1 to infinity e squared over n, all raised to the nth power, because I would multiply those exponents and I would get back to that. So I could use the root test. That looks pretty easy. So I'm going to take the limit as n approaches infinity of the nth root of e squared over n to the nth power. I'm going to take the absolute value because I don't want to have any imaginaries popping up on me. Okay, what does that equal to? I'll have the limit as n approaches infinity, the nth root of the power of n. I have that. As n gets larger and larger, because e squared is around 10, it's not varying, that value is 0, which is less than 1. So again, the series converges absolutely by the root test. My challenge is, could you possibly have used the ratio test? You might try it and see what you can come up with. Let's look at these examples. Well, number 3 just screams root test because everything is to the nth power. So I'm going to take the limit as n approaches infinity of the nth root of the absolute value of my series. That's going to give me the limit as n approaches infinity of 3 over n plus 1, and the limit as n approaches infinity is going to be 0, which is less than 1. So converges absolutely by the root test. Pretty easy. So looking at example 4, kind of looks like the root test. Okay, that might come in handy. We've actually proven that limit before, but let's see if we could possibly use that. Well, it looks like the root test should be good. So if I take the limit as n approaches infinity of the nth root of the absolute value, 1 minus 3 over n to the n power. That's going to be the limit as n approaches infinity of 1 minus 3 over n. Well, this goes to 0, and that equals to 1. What does that tell you? Nothing. Absolutely nothing. It's inconclusive. If we get a limit equal to 1 with the ratio or the root test, we have to try something else. So, I think I will, let's see, I really don't think the ratio test would work any better. Doesn't look like anything else. Well, I know. How about the nth term test? The nth term test says take the limit as n approaches infinity of just that. I thought I was going to get away with just 1, but I've got that nth term. And that's where we need to remember this. Okay, so do you see how that x is now 3, but everything else matches, so it's going to be e cubed. And again, you can go way back to the chapter where we did L'Hopital's rule, and you will see that we actually did that limit. So that's e cubed, which is not 0. What does that tell us? That means that this series diverges And what test were we using? The nth term test. And I guess truthfully, we really should start with that first, because if that doesn't equal to 0, you're done. Unfortunately, most of the time, the limit does equal to 0, and you have to try something else anyway. These next two problems, you should see factorials. And when you see factorials, you should think, I've got to use the ratio test. So that's what we're going to do. So we take the limit as n approaches infinity. And remember, we're going to, instead of the ratio of the n plus 1 term over the nth term, we're going to multiply by that reciprocal. So everywhere you see an n, you replace it with n plus 1. And then we're going to multiply by the reciprocal of the original series. Well, I know that n plus 1 factorial is n plus 1 times n factorial, so I can reduce that and be left with n plus 1. What else can I do? Well, I kind of see an n plus 1 and an n plus 1. Let's see, so what do I have? I have n plus 1 to the n plus 1 power over n plus 1 to the first power. Well, I have the same base. So if I have the same base, I can keep the base and subtract the exponents. So if I subtract those, what would I be left with? So again, I'm looking at this, and that actually reduces to n plus 1 to just the nth term. And I still have this in the denominator. Yuck. I don't know about that. Let's see. I have a lot of n's everywhere. What if I wrote this as n plus 1 over n all to the nth power? That does not look any better. Let me try one more thing. Okay, so if I divide each of these by n over n is 1, plus 1 over n to the nth power. Well, doesn't that look just like what we saw up here? So I have a 1 there, so that's going to be a 1 there. And again, if you want to see that derivation, go back to your notes. We've already done that. So this is just e to the first power. I'm using the ratio test. That's greater than 1. And that says if our ratio is greater than 1, then the series diverges. Example 6. Ooh, lots of factorials. So same thing. I'm going to have the limit as n approaches infinity of the absolute value. Everywhere there is an n, put an n plus 1, and that's all squared, divided by 3 times n plus 1 factorial, and then multiply by the reciprocal of the original. I'm just going to take a little bit and kind of write this all out. So n plus 1 factorial squared means I have 2 of those. On top I have 3n factorial. On the bottom, that's n factorial times n factorial. But what is this? Well, if I distribute, it's 3n plus 3 factorial, which means that would be 3n plus 3 times 3n plus 2 times 3n plus 1, and I'm running out of room, times 3n, and I'm going to stop there. All right, why am I going to stop there? Because those are the same. Okay, this and this reduce to just n plus 1. This reduces to just n plus 1. And let's see what else I have left. I have n plus 1 times n plus 1 on top. On the bottom, What's that limit? Well, let's look at the powers. Here I have an n squared, and on the bottom I'm going to have 27n cubed. So I have a higher power on the bottom. What is that limit? That limit is 0. So what can we conclude? If that is 0, which is less than 1, then we can say the series converges by the ratio test. When you're working your homework, you're probably going to recall or need to recall that the limit of the nth root of n is equal to 1. Make sure you know when the ratio test and the root test converge or diverge. They're the same. Less than 1 converges, greater than 1 diverges, equal to 1, inconclusive, try again.